We are now going to talk about similarity and specifically right triangles. Before we do that, though, we need to talk about one term called the geometric mean. This is different from our arithmetic or algebraic geometric mean, where you find the average. The geometric mean is a positive number of x such that a over x is equal to x over b. So let's look at a couple examples. Find the geometric mean of 6 and 15. I would set up as a proportion 6 over x is equal to x over 15. To solve proportions, we cross multiply, so we get x squared equals 90. And then to get rid of the square, we square root. X is a square root of 90, or simplified, x is 3 square root 10. Now it doesn't matter if we put 15 to x or 6 to x, whichever one we want to put first is fine. It won't affect our outcome. So same thing here. I did 4 over x equals x over 18. But if I decided to do 18 over x equals x over 4, we would have still come up with the same answer, because we will cross multiply. X squared is 72. So we square root x is square root of 72. And simplified, x equals 6 square root of 2. Your turn. Pause the video, find the geometric mean of 7 and 15 in simplified form and 4 and 11. When we find 7 and 15, we get x equals the square root of 105. And 4 and 11, x equals the square root of 44, or 2 square root 11. Right triangle similarity. Our only theorem for today is theorem 7.4. This says that the altitude to the hypotenuse, now remember altitude is a line from the vertex to the opposite side that hits at a 90-degree angle. So the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. So if we look at our original triangle ACB in blue, I drew the altitude in red CD to show specifically where the altitude would be, and then to show the two triangles it creates. It creates triangle CAD and CBD when it divides it into two similar triangles. Now, when we talk about similarity, if we look at ABC, our triangle, the similar triangle is going to be ACD. And the smaller one, the similar triangle, is going to be CBD. Because we need to put the triangles in order from least to greatest, or the sides in order as far as their size. So if we look at AB in the first triangle, that's the hypotenuse. So AC is the hypotenuse in the second triangle, and CB is the hypotenuse in the third triangle. If you have questions, please ask in class, but take a second, look at this, and see if you can tell how the triangles are similar by using rotations and reflections to see how they relate to each other. So we're going to use this to solve. So I want to solve for the variables, and this can often be hard when I'm looking at a set of triangles because I have three different triangles within this diagram. I have the big triangle and the two smaller ones, which are all similar, proportional to each other. So when I use these, I often draw the triangle separately. So I have the small triangle, the medium triangle, and the larger triangle. By drawing these triangles, I can get an idea of how they relate and how each side relates. So if I look at the first one, I need to solve for x. Well, I can see that in the smallest triangle, 4 is related to x in the biggest triangle. And the hypotenuse, or x, in the smallest triangle is related to 16 in the bigger triangle. So I can set up a proportion. By cross multiplying, I get x squared equals 64, so x is 8. Y, I notice that y in the medium triangle is related to 4 in the smaller triangle, so 4 to y. And then again in that smaller triangle, y is related to 12 in the medium triangle. 4 to y equals y to 12.
Pardon the interruption, Ms. Harris, for the main office.
I apologize for the interruption, but we were saying that 4 to y is equal to y to 12, and when we cross multiply, we get y squared is 48, or y is 4 square root of 3, or the square root of 48. Lastly, we have to find z. Well, we see z in the medium and the bigger triangle. So 12 is to z, as z is to 16. So 12 in the smaller one to z in the bigger one, as z in the smaller one to 16 in the bigger one. Cross multiply, z squared is 192, so the square root of 192 simplifies to 8 square root 3. If we look at the second diagram, notice that we were only solving for two variables, but we're also missing a side. So again, I drew the triangles separately to kind of see relations. If I look, I see x in both the smaller and the biggest triangle. So I'm going to set up my proportion for x. 4 is to x, as x is to 9. Cross multiply, x squared is 36, so x is 6. For y, I notice it in the smallest triangle and the medium triangle. So 4 is to y, as y is to 5. Cross multiply and simplify. Y is 2 square root 5. We also have some corollaries that relate to theorem 7.4. The first one says the length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. Well, that's a lot of words. So, what it's saying is the hypotenuse CD, the altitude CD is the geometric mean of the two pieces of the hypotenuse, AD and DB. So you can see how it's written in our fraction. To find the altitude, as long as we know the two segments of the hypotenuse, we can find the length of the altitude. The second corollary says the altitude to the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the triangle is the geometric mean of the length of the hypotenuse and the length of the segment of the hypotenuse adjacent to the leg. Again, this is a lot of information. What this tells us is we can find, given the hypotenuse, we can find the length of the legs. Because the length of the leg, for example, AC, is the geometric mean of AB, the entire hypotenuse, to the piece of the hypotenuse touching the leg, AD. So this length is the geometric mean of the whole to the part. And we can do the other side too. This leg is the geometric mean of the whole hypotenuse to the segment of the leg that touches that base, touches that side. So a couple more examples to look at. Solve for the variable. Well, we know that the altitude is the geometric mean of the two pieces of the hypotenuse. So 8 is to x, as x is to 2. X squared is 16, so our altitude is 4. On the second one, we're going to have to do two problems. First one with x. X is the geometric mean of the piece of the hypotenuse closest to the side, 5, and the whole hypotenuse, 13. So x squared is 65, x is the square root of 65. Y is the geometric mean of the side of the piece of the hypotenuse, 8, that touches the side, and the whole hypotenuse of 13. So we get y squared is 104. Y is 2 square root 26. And that's it. You can cross off things on your to-do list. You have nothing left for this class. Thank you.